So more with our electrophilic addition. We're going to be going into chapter 24 because really what we're concerned about is our Diels-Alder. So when we look at our Diels-Alder, we've got some kind of naming pieces that come out of this. First and foremost, we have what is known as the diene because there are two double bonds. So diene. And then we also get the dienophile, which similar to the nucleophile or the electrophile, that would be the species that is attracted to the diene. And there's our representation of them. So one of the things as far as pattern recognition goes that I want you to try and acknowledge and kind of discover as we're going through here is to identify the bonds that are broken and bonds that are formed when we're looking at an overall reaction. So if we were to go through and address this, one of the things that does make it more challenging is trying to acknowledge where these pieces came from and where they went to. So this is the default format for showing the Diels-Alder reaction, which means that when you look at an exam, you should probably twist and rotate the structures because you probably won't be looking at things as a default. But this helps to kind of color code that patterning. So you've got the diene shown in red, the skeleton being reflected in the cyclohexene, and then the dienophile being shown in blue, and you can see its piece remaining at the other end. If we were to go through and address our bonds that were broken and formed, we might go through and note that the pi bonds were all broken, and that what was formed was a new sigma bond, and a quote-unquote new pi bond. And if we think back to the analysis, at least the analysis that I gave in first semester for our SN1 and our SN2 reactions, or ultimately our substitutions, we really only had one bond broken and one bond formed, which meant it was relatively easy to kind of parse together what are the possible mechanisms that could come out of that. And that's where we get SN1 and SN2. In this case, we've got 6 separate things happening. The order in which those 6 different things happen could be very confusing to parse through and to organize. So this is where it can be helpful if we try and break things apart a little bit and try and address kind of the big changes that occurred. So charges, partial charges, resonance, all that fun stuff. And if we use that resonance argument, we can draw some interesting conclusions. So if I was to use resonance, I could say take that top pi bond in the diene, and I could move those electrons to that carbon, put a positive charge there. And I could take the electrons in the other pi bond and put them out here, okay? So all I've done is drawn a resonance, and admittedly, it's a horrible resonance, tons of charge in there. But what we're using this is this charge to help us try and think about how the reaction could occur. And if we do the same thing for the dienophile, negative and positive, this helps to actually show where those pieces are aligning. We're taking a negative to positive to form that new sigma bond. We're taking a negative to positive to form that new pi bond. And we're taking a negative to a positive to form that sigma bond. So really, we're forming 1 sigma bond, 2 sigma bonds, and 1 pi bond. So the system that we went through and said there's 6 different things happening, we can now say is actually just 3. That's pretty cool. Add to that pi bonds have resonance. The difference between the structure on our right, pi bond being shown as a double bond versus as the charges are just resonance structures and are therefore one and the same, really just means all I've done in the Diels-Alder reaction is formed 2 new bonds, sigma 1 and sigma 2. Okay? Being named 1 and 2 just as an arbitrary naming system. So this takes us back to the parallels that we see within substitution, and that we're really only forming 2 bonds. So now it's a question of the order in which those 2 bonds can form. So that order is your when, it's the how the mechanism works, okay? And so really there's only 2 ways that this could happen. Sigma 1, then sigma 2. So stepwise, like the SN1, or make sigma 1 and sigma 2 at the exact same instant simultaneously, similar to what we saw with an SN2. And so when this reaction was discussed and analyzed, these were the two primary categories. And what we discuss in the lab is trying to design an experiment that would allow us at a very, very, very simple level to address these two mechanisms. What we end up discovering is that really it only happens one way. Okay, so where I called it DA for Diels-Alder 1 and 2, it's really just Diels-Alder. Okay, we make sigma 1 and sigma 2 simultaneously. As a side note, this can also be referenced as concerted, and it can be referenced as synchronous or asynchronous. The synchronous versus asynchronous, I just want you to be aware of as terms, that it is something that is still actively kind of looked at and evaluated, and to really address that, you have to use molecular orbital theory. So we aren't going to go there. We're really just going to address that this is a concerted mechanism, that those bonds form at the exact same instant. Right? So what we're doing is taking the electrons from one pi bond and sharing them with the other. Right? Then that pi bond rotates, and then that pi bond. If we go through with how I drew that, right, starting with the red, then with the purple, and then with the blue, right, let's think about how this reaction would most likely occur. Does it make sense to start at the dienophile? No. Why not? The diene has more electrons, so arguably how I drew that was incorrect. I should have drawn pi bond attack, pi bond attack, whoops, pi bond attack, and then pi bond shift. And for those of you who are really paying attention, you might notice, didn't I draw the exact same thing? Yes, but the intent behind how you draw it does become important and has valid conclusions. Okay? So when you try and draw things, both in mechanisms and in structures, you want to be as accurate as possible to the real three-dimensional world. Okay? Because it does have implications for your end goals and conclusions. So for this to occur, we're taking the p orbitals of our dienophile, and we are reacting those p orbitals with the p orbitals of our diene. Okay? For that to happen, the orbitals must overlap, right? Which means, and this becomes a challenging thing to draw, that if we took this structure and we turned it on its side, oh yeah, we would have these p orbitals now straight up and down, and that if we drew in the dienophile, the p orbitals are going to be straight up and down as well. These p orbitals need to overlap with each other, which means they could either overlap from under the diene, or they could overlap from above, which means we do get two potential products coming out of these. Just like with all of our addition reactions, we get the potential for multiple products because we're reacting a pi bond, and pi electrons are both above and below the plane of the molecule. Oh, and now the real fun part, okay? Because that in and of itself at least gets us to the two products. The next part that comes out of this is addressing where each of the atoms that are connected to these end up going. And you might say, well, I don't really care about those. And what you're probably looking at or considering is the atoms that are shown. What you probably aren't considering is that we also have atoms that aren't shown. And those atoms, if they are different from each other, have the potential to generate stereocenters at each and every single one of those positions. Right? Before we panic too much and go 2 to the 4, that's a ridiculous, I can't do the math, 64, a large number of possible products, remember that it happens simultaneously, which means a lot of those things get limited. Okay? But those limitations come from understanding how these orbitals overlap. When we go through and have these orbitals come in contact with each other, these orbitals have to hook up. As they hook up, this hydrogen is going to drive down away from that forming bond. What are these hydrogens going to do? Okay. Well, this inner one can't go down, because if it goes down, it directly hits the system underneath. Okay. Which means that inner hydrogen must go upwards. That means this outer hydrogen goes downwards. The hydrogen or a dienophile that went down, that means this other hydrogen must go up. So if we're looking at the spatial alignment of where our new bond is forming, how our orbitals overlap, that can help us to dictate where those individual groups go. And in this particular example, we don't care because we didn't form stereocenters. But what happens if we do form a stereocenter? Right? For instance, if I put a methyl here, okay, which direction is it going to go? Well, that means we'd end up with a methyl out here. We would either have it wedged or we would have it dashed. And because this reaction could happen from the top or the bottom, both of these are potential results, and we wouldn't really be able to detect that difference. So a single methyl on there doesn't really change anything. But what happens if I add another methyl? Okay. Now that's going to change that dynamic, and I have to be a little bit more cognizant. Instead of it being wedged and dashed as possibilities, I also have wedged and dashed as possibilities here. Do they align where I get a wedge and a dash as a possibility? Do they align where I get dash and dash? Do they align where I get wedge and wedge? Okay, whoops, that meant to be a different color. So we get all of those possible combinations that could come out of this. They're possible. That doesn't mean they happen. How do we know what happens? That comes back to addressing, again, the reaction in that dynamic. Okay? We drew it down below. If we have the methyl groups aimed outwards, the inner atom needs to rotate up because my dienophile is coming in from the bottom, which means this atom is going to rotate down, CH3. What happens to the hydrogen on the inside on the other one? Same deal, it has to rotate up, which means that CH3 rotates down. I'm going to get the situation where they're dashed. Okay? Couldn't I have just as easily had the pi bond come in from above? Yep. And if I go through and do that, that's going to force those inner hydrogens down away from the new sigma bond, which then means my CH3s will both be wedged. Note that wherever my CH3s are aimed, they align the same as long as their relative position to the hydrogens are the same. What do I mean? Hydrogens are inwards, the methyls are outwards, which means the rotation is the same. If I changed it where the methyl was inwards and the hydrogen was outwards, now the methyls are going to go to opposite locations. One will be wedged, one will be dashed, depending on that attack. This is insanely difficult to draw, and I would argue that you really should be pulling out a model kit, and that's what those other videos try to get you to do, is to manipulate a pseudo model to manipulate these and see those structures. It takes practice to get used to seeing these three-dimensional objects, and it's really something that's a lot easier to do when I'm there in person to force you to kind of manipulate it. Oh well, we got to do the best we can. To that end, that's where it comes in with practice. Curses, that's stupid pictures floating over the top of that. And I'll fix that in a second. So what we've got here is 1, 2, 3, 4, 5 questions. You should go through and try and do some work on these to figure out what you think the answers are. Okay, so this is where I would recommend, well, we won't quite recommend yet. Let me move my floating picture so that you can see that. Note that that methyl is floating in there. Okay, it's floating to the outside. That's important to note when you try and go through and solve these. And can I move the picture? We'll just cover Diels. Sorry, Diels. Deal with it. And you'll see why here. So go ahead, hit the pause, go through and try and solve as many of these as you can. Okay, with that, we'll throw in a little bit of a hint. We have this sigma up, sigma down thing that could help you go through and deal with the alignment. That sigma down and up has to do with where you're deciding to do that alignment, be it a top down or a bottom up kind of reaction. It is challenging, but I think that little red box can help you kind of predict it. So with that, I'm going to say go ahead and hit pause again and see if you can get a little bit further. And then with that, I will try and walk through these as best I can, as quickly as I can, because I can't pause the video while I'm solving as needed. So the first thing that I'm going to do, addressed where my diene and my dienophile are. So I'm following that core kind of pattern. So nothing fancy has changed here. So there we go. There's the basic structure. I have the new pi bond that's formed, and it's formed on the diene side of it. Okay. I have a methyl group that needs to be placed in there, and then I have these carbonyls that need to also be placed. Okay. Once I've done that, that might whittle away enough answers that I'm comfortable enough with a guess. But I would bet if it's a multiple choice, you're probably going to see a lot of wedges and dashes, because those carbons, where those groups are located, are all stereocenters. The first thing that I'm going to jump on is note that these guys are aimed the same direction. Okay? It's a cis dienophile. Because it all happens at once, I don't allow for bond rotation, which means I'm going to go through and say that those are dashed. Remember, because this is a Diels-Alder reaction, there is just as likely the possibility where they are wedged where it came in from the top part of the structure. Okay, but they need to be the same direction. The next part is addressing where that methyl went. Okay, well, I prefer seeing the sigma down interaction. So these are coming in down, which is why those ended up being dashed in the final product, which means this hydrogen has to get forced upwards. Okay, which means that this guy gets aimed down. The end result, that has to come in dashed. If we'd flipped it and it came in the other direction, we're going to note that it's going to come up wedged. Okay, and we end up with our final product. Okay, or final products, because it's two. If we move to the next one, that one becomes a little bit more challenging. First and foremost, because the core structure of my diene and my dienophile has been flipped on me. Okay, I'm probably going to reflex to drawing it this way anyway. Okay, where I've got it aligned, matching that standard format. When I went through and did the reaction, though, I only react one of those pi bonds, which means the other one is still there. This becomes extra tricky because the structure is now symmetrical, so we have to be a little bit more careful with this. Okay? I also have that COOH, okay, or rather a carboxylic acid. I have to think a little bit there. I'm just going to draw it and say COOH. Right? And where this is going to become important is that I have to understand how that affects the rest of this. That carbon becomes positive, which means these electrons withdraw out, which means this carbon is my positive. Right? Why does that become important? If we go through and look at the other structure, it is also asymmetric. That nitrogen with a lone pair of electrons can donate in, negative, okay, puts the negative charge on that carbon. I need to make sure that those two carbons tie to each other and these two carbons tie to each other. Okay? I know tons of stuff drawn on there, but that's what we're trying to depict, is recognize that that resonance does contribute to the alignment of these things, which means my NH2 is going to end up there, and my methyl is going to end up down here. I don't have to worry about a stereocenter where the COOH is, because that is an sp2 carbon, so that's nice. I do have to worry about stereochemistry about those two positions. As we go through and do this, I again prefer the sigma down aspects behind this. That forces the NH2 up, and it forces the CH3 up. Okay, again, two products. This is one that I can get away with saying plus an enantiomer. Okay, so lots of moving pieces within that, but hopefully you can see how that alignment works. You can see that kind of red box helping to predict those. In each of these, you will note that we end up with a cyclohexene, which means we get chairs, which means we could have shown the products in the formation of chairs, which is extra crappy because now we'd have to depict out those different representations, and chairs are always a bit of a challenge to see. I personally would attempt to draw my Diels-Alder product first. Okay. My COs are going to be on the same side. Again, I prefer that down angle for my sigma bond. This CH3 is going to be up, this CH3 is going to be down, and so that's what I would be looking at. If I went through to try and see, I'm going to pick the easiest ones, down, 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 down. That's where I can be like F, that didn't help, right? My methyls are up, down, up, down, up. Really? Man, couldn't have made it any easier, right? Right. Now I'm going to try and find relative positions of the pi bond to my methyls. So there's my pi bond, position 1, 2. That looks okay. Pi bond 1, 2. Pi bond 1, 2. That actually looks okay also. Did I do something really obnoxious and say all of the answers were valid? Oh, whoa. Hello. Where's that aimed? This one's up. That one's down. That doesn't work. Okay. So B is indeed wrong because the carbonyls are aimed the wrong direction. They both have to be aimed the same way, be it both down or both up. Okay, so that one would be incorrect. As we go through and look at the others, I have a sneaking suspicion that A and C are enantiomers of each other, or chair flips. We turn. Let's take a look at A. Oh, this is where pause would come in handy. And I also have to go to the bathroom, and I can't pause, which means this is an awesome opportunity that you should ask questions about, Jiminy, Christmas, online. Explain the difference in reactivity between the following two dienes, okay? What's going to happen between these two is that if we note that this is cyclic, and this one's acyclic, okay, why does that become important? Look at how the diene is oriented in each of our questions. The diene is oriented in what is known as that S-cis conformation. That S-cis is required for this to happen concertedly. Right? If we take a look at A down below, that is not S-cis. That is the double bonds on opposite sides of that sigma bond. That's the S. in that statement. So those are not aligned to react, so not reactive. And if we look at B, you'd be like, well, but they're the same in B. But remember, this was not cyclic, which means I can freely rotate about that bond, which means B will be allowed to react. It's just not in its active state right now. Okay? So this probably needs a little bit of heat to allow a sigma bond rotation. With that sigma bond rotation, we can get into the S-cis, and we'd be able to run that reaction. As far as predicting starting materials for the following compound, sorry, I'm picking up the pace because it's getting more and more urgent. We can split this in that fashion, in which case we would end up with this structure, CN, CN, and then we'd be saying that remaining piece would have to come in as a triple bond. Okay? So that could work out for us. Or we could have split it the other direction. Oof. Okay? Where we could end up with that structure and then triple bond CN, CN. So we really get two potential ways that we could have done this. Is one way better than the other? Right? Well, if you see multiple ways, gut response, pick the one you didn't see first. Right? Because you probably saw it first because it was organized so that you would see the wrong answer first. Right? And it turns out that that is the case here. B is the better synthesis here, and it has to do with the activity. The diene acts better as the nucleophile, as the source of electrons. The dienophile acts better or faster as the electrophile or the receiver of electrons. Those CNs, being electron withdrawing groups, make that reaction happen faster when they are connected to the dienophile and not the diene. And with that, I'm going to say apologies for the which of the following is the correct representation, though my instinct right now is saying AC. A little nervous about that. A and C are the same thing. But you should ask about that in class if you are not 100% confident behind my answer. And I don't blame you because you're moving to massively three-dimensional objects. And with that, thank you for listening. I do appreciate it and apologize, but I really got to stop. Oh, where's my stop button? Let me stop.